Okay, Newton's three laws of motion. This is the practice worksheet. Okay, it's not mine. I must give credit to Stephen Murray, very impressive physics teacher who has created these wonderful worksheets, and I'm going to borrow some of them. So the first one, we have notes on Isaac Newton, some notes on first law, second law, and third law, some details about inertia, some details on force, net force, which is the next journal entry you're going to learn about as well. And then some Newton's second law, the formula, and how to apply it. And lots of little notes. So this is a fabulous resource for, if you didn't understand the way I taught it, here's another way to learn it. On the back side, okay, how this worksheet works. It's divided into sections. So this first section is matching. This is all one section right here. So F, the uppercase F stands for force. Force is measured in newtons. 6 newtons is the answer you'd write right there, and you can cross that one off. Okay? As you go through all these, you should know all those, what those mean, except the very last one. We haven't taught that one yet. I haven't taught you that one yet. And that one is called momentum. And momentum units of measure, that's the 23 kilogram meters per second. The second section is also matching. I recommend doing the letters. So inertia, mass, gravity, net force, and force. Match them with their definitions. And you can put a little letter next to each one of those. Here, number these from least being 1 to most being 5 of inertia. So remember we talked about inertia and qualities of inertia. You can read a little bit more about here. Give you some inspiration right there. Least to most inertia. Newton's three laws of motion, whether it's the first, second, or third law that applies in each scenario. So for a few notes, remember the first law. Objects at rest or in motion stay that way. Remember that in motion is a constant velocity until unbalanced force is applied. Okay. Newton's second law is the formula F equals ma. So if you're dealing with a situation where we change the mass or we change the force and the acceleration is altered by that, then you got the second law going on. Third law, remember with this one, there has to be two objects pushing each other. Okay, so the first one, when you put a book on a table, the table pushes on the book. So the book and the table, and they're pushing on each other, that's definitely Newton's third law. Okay, understanding net force. So we have here a scenario, we have this object with a mass, 30 newtons pulling to the left, 25 newtons pulling to the right. So first question I have, what is the net force? Okay, so we've got 25 to the right, 30 to the left. They kind of cancel out a little bit there. That 25 cancels out 25 of those. So you end up with 5 newtons going to the left. That's your net force. So the question asks, which way or which direction will it accelerate? It will accelerate that direction, to the left. Okay, continue with the other two. All right, here we have 3 problems talking about net force. And then we've got 3 problems dealing with F equals ma. Okay, so the first one, a sled is being pulled to the left by 5 dogs. Each dog pulling with 6 newtons of force. Let's find the net force. So we've got 5 dogs going left that way. So 1, 2, 3, 4, 5. Give them tails, make them look like dogs as much as I can. 1, 2, 3, 4, 5 dogs. Each pulling with 6 newtons. So he's pulling with 6 newtons. He's pulling with 6 newtons, 6 newtons, 6 newtons, and 6 newtons. And they're all going the same direction to the left. And it asks the question, what is the net force? Well, if they're all going the same direction, we add them up. 6 times 5, 30 newtons to the left. Okay, so continue with the other 2. Over here, simple problem-solving process. Use your formula, F equals ma. If you need to rearrange that, there's your triangle. M and A are side by side. F is on top. Problem-solving process. Don't forget your units of measure if you need to. Always consult back to the front. On the front side here, it shows the formula. Units of measure for mass in kilograms. Units of measure for acceleration, meters per second squared. And Newton for force. Newtons are the unit of measure for force. That's meters per second squared. Okay? So, good luck working through that worksheets. Do the best you can. And pause this video and then come back to see how to check your answers. Pause the video to check your answers. Okay, so here we go, checking your answers. M, this is measuring mass. Mass is measured in kilograms, that's the 125 kilograms. A is acceleration. Acceleration units of measure are meters per second squared. So that's the 3 meters per second squared. The squared goes with acceleration. V for velocity. Velocity measured in meters per second. Here we go, the 29 meters per second. And our last one, D for distance. Distance measured in meters, the 228 meters. Second section. Okay, inertia, mass, gravity, net force, and force. This one, I'll only do a few of them because you should be able to figure these out with the notes on the front side. The definitions are right there. You just have to find them. Okay? So, we'll go with the hardest one. I think this one's the hardest one. Force. Force, normal definition is a push or pull. That's your most simple definition for force. But that one's not offered here. So is the ability of an object to resist a change in motion? No. Total of all the forces acting on an object? That's not force. That's net force. The amount of matter in an object, the force pulling all objects towards each other, or an action that can cause a motion. There you go. Action that can cause motion, force. Okay, least to most inertia. How much inertia an object has totally depends on its mass. So, least mass, whether it's moving or whether it's not, of all these objects is the feather. The most one is going to be your train. Put them in order accordingly for the rest of them. Okay, the 3 laws. This is probably the trickiest question, trickiest section of the worksheet. So we did the first one already. The second one, a person is pushed forward in their seatbelt when a car stops. This one's really confusing, actually. So imagine you're driving along and you hit the brakes and you slide forward in your seat. This is what it's referring to, okay? When you're driving in the car, you're moving with the car. The car stops and you want to keep moving. So that's Newton's first law of motion. Because you are an object in motion and want to stay in motion, even though the car around you is coming to a stop. Okay? A larger car takes more force to move. Okay, larger car, we're talking about mass, force, and to move something means to accelerate it. So F equals ma, Newton's second law. A person leans on a wall and the wall pushes back. 2 objects pushing against each other, third law. A brick sits on a table until you push it. So there's an object at rest that stays at rest until force is applied. First law. Okay. So this one, pretty easy. My net force, I've got 6 to the left, 8 to the right, 2 newtons to the right. So it will accelerate to the right. This one will have a greater acceleration, most likely, assuming they have the same mass. This one will have a smaller acceleration because it's got smaller force. What about that third one? 15 newtons this direction, 15 newtons that direction. Which way will accelerate? Will not accelerate. It will not accelerate. It has two options. It could either be at rest or it could have a constant velocity. We don't know until we know more information about the motion. It could be either scenario. It could be it's already moving and there's the force of the engine and air resistance pushing it, or it could be at rest and there's two things pulling at it that are balanced out. Okay. On these problems, 20 kilogram bike, it's measuring the mass, 10 meters per second squared, measuring the acceleration. Question is asking for the force. If force is the question, do we need to rearrange the formula? No, we do not. So you can plug in your numbers. Remember, your units of measure for your answer are going to be newtons. Okay. Next, if a person is pushing on a car with a force of 40 newtons, newtons measurement for force, accelerate 0.5 meters per second squared. Meters per second squared is acceleration. Question is asking for the mass of the car. If F equals ma, do we need to rearrange the formula if m is the question? Yes, we do. So, refer to your triangle. Rearrange your formula to solve for m. Mass is measured in kilograms. Okay, what is acceleration? 3 kilogram rock, kilograms measures mass. That is thrown with a force of 18 newtons. 18 newtons is the force. Question is asking for the acceleration. F equals ma. If a is the question, we do need to rearrange the formula. So again, refer to your magic triangle right there. And remember that the units of measure for acceleration are meters per second squared. Be sure to show your answers with each of those. Calculate them out, show your answers. Here we have a person pulls on a car with a force of 10 newtons, pulls to the right with 10 newtons, and a second person pulls to the left with 3 newtons. What is the net force? So this is a great opportunity to just draw for a body diagram. We have here 10 newtons to the right. We have here 3 newtons to the left. Notice how I drew this one larger. We do that with these vector diagrams. The longer the arrow, the stronger the force. So longer arrow, it's a label though, 10 newtons and 3 newtons. So the net force is my question. Well, if I've got 10 to the right, 3 to the left, they're going opposite directions, we subtract. So we end up with 7 newtons, and the larger number is going to the right, so 7 newtons to the right. Here we have 2 newtons and 6 newtons pulling to the right, and 4 newtons pulling to the left. And then we have the mass of the object, so 0.5 kilograms. Ask for, telling us 2 newtons to the right, and 6 newtons to the right, and 4 newtons to the left. The net force. So, do I need this? Nope. The mass is extra information. I just need to do these. So 2 and 6 are going the same direction, so I'm going to add those up. So this is actually 8 newtons total going to the right, and 4 newtons going to the left. We're going to subtract 8 and 4. I end up with 4 newtons to the right for my net force. Hopefully, as you work through these other problems, if you're not quite sure, go find a neighbor, someone else has worked through the problems, and check your answers.